Welcome to Chemistry 101, Selected Problems for Chapter 6. Benzene is a known carcinogen that burns in air according to the following equation. What is the mole ratio of oxygen to benzene? Well, the mole equation is the big coefficients in front of the compound. So here we have 2 moles of benzene for 15 mole of oxygen. So that would be the mole ratio. And these equal each other, and you'll see in dimensional analysis, those are conversion factors. And that means depending on what we need, we can do 2 mole of benzene for 15 mole of oxygen. Or if we have to flip it and we need the mole of benzene on the bottom, we can say 15 mole of oxygen for 2 mole of benzene, because these are equal, so that means they're like 1. So 5 over 5 or 5 over 5 is still 1. Okay, so that's saying they're the same thing when we say something equals. How many moles of oxygen are required to react with each mole of benzene? So that's basically 15 moles of oxygen are required to react with 2 moles. So then you divide that by 2, 7.5 moles of oxygen are required to react with each mole of benzene. How many moles of oxygen are required to react with 0.38 moles? Now this is a given, so let's do the dimensional analysis. 0.38 mole of C6H6 over 1. And then we copy those letters down. Mole of benzene, and it's asking for how many moles, this is your question, of oxygen. So we need to go to mole of oxygen, and now you know that you can do these conversion factors. So here we have, for 2 moles of benzene, we have 15 moles of oxygen. And so these are going to cancel out, and you're going to left with moles of oxygen. So when you get your calculator now, you know that you take 0.38 times 15 divided by 2, and that's 2.85 mole of oxygen. And that's how you solve that problem using these coefficients. Mole ratios. This is stoichiometry. Okay, so when copper 2 sulfate pentahydrate is heated, it decomposes to the hydrated form. What is the molar mass of copper sulfate pentahydrate? Okay, so well, you got to get your periodic table out. You got 1 copper. So let's look at this. Copper is 63.546. You have 1 sulfur, that is 32.066. You have 4 oxygens here, so that's 4 times 16. Then you have 5 times 2, you have 10 hydrogens, so it's 10 times 1.008, and then you have 5 oxygens here, so that's 5 times 16. And so the formula weight, when you get out your periodic table or your calculator, 5 plus 4 oxygens times 16 plus 10 times 1.008 hydrogens plus 32.066 plus 63.546, you get 249.69 grams per mole. What is the molar mass of copper sulfate? Well, it's going to be less, isn't it? So you have 4 oxygens times 16, 4 times 16 plus 32.066 for sulfur plus 63.546 for copper, 159.61 grams per mole. Now, you're going to use those masses whenever you're having to convert moles to grams. So we have a number with a unit, that's where we start. If 1 gram of copper sulfate pentahydrate, and you always want to write the substances down because sometimes you're going to change them, is decomposed to copper sulfate, predict the mass of the remaining copper sulfate. So if you take 1 gram, so what's our plan? Our conversion factor plan. You got to go from grams of copper sulfate pentahydrate, decomposed to copper sulfate, predict the mass of remaining. Decomposed. Well, then you just go to, I don't really know how to answer that really. Because if you have 1 gram decomposed to copper sulfate, predict the mass of the remaining copper pentahydrate. I guess it would be none. I mean, I don't know how much you're starting with. Is there something I'm missing here? We didn't start with a mass. So predict the mass of the remaining. So I don't know. I think that's worded weird. So we'll just skip on. All right. When active metals such as sodium are exposed to air, they quickly form a coating of metal oxide. Suppose a piece of metal, so it contains 2.05 grams of mass after being exposed to air. All right, so that would be the product here. 2.05 grams of mass after being exposed to air. Assume that the gain is attributed. What is the mass of oxygen? So what's the mass of oxygen reacted with sodium? All right, so this is what we start with, our number with a unit, 2.05 grams of sodium oxide. And then you're going to do grams of sodium oxide. You're always going to have to go to moles. So you're going to have to go to moles of sodium oxide. And then you have to change substances. We want to go from grams of sodium oxide to a mass of oxygen. So we copy this down, mole of sodium oxide, and we need to go to mole of oxygen. But it's asking for the mass of oxygen. So we got to copy mole of oxygen to gram of oxygen. Now, this is molar mass. So gram per mole. Gram of sodium oxide for 1 mole of sodium oxide. We get that molar mass from the periodic table. So sodium is 23. There's 2 of them plus 16. So we have 62.00 grams of sodium oxide for 1 mole. And here we get the coefficients. And this is in a balanced equation. So we have our balanced reaction. And so what's in front of sodium oxide is 2. And what's in front of oxygen? 1. And then we do the molar mass here, 1 mole of oxygen. There's 2 at 16, that's 32.00 gram of oxygen. So now you go 2.05 divided by 62 divided by 2 times 32. And so the answer is 0.529 grams of oxygen gas will react with sodium metal to form 2.05 grams of sodium oxide. What is the mass of sodium reacted? Well, in that case, you just backtrack here and you see how you have, you go from mole of sodium oxide, now you want to go to mole of sodium. And so you can change the names of the elements and compounds as long as you're going from mole to mole, but that's not what you want. It asks for mass, so it wants gram. So you're going to have to copy mole of sodium on bottom, and you can go from mole to gram using the periodic table. So here you have 2 in front of sodium oxide. Here you have 4 in front of sodium. And then for 1 mole of sodium, you have 23.00 grams of sodium. So now you can do 2.05 divided by 62 times 4 divided by 2 times 23. 1.52 grams of sodium. For each of the following unbalanced equations, so you need a balanced equation, you always start with the balanced equation. We need to balance and then determine how many grams of the second reagent. So they're asking for the second reagent here, how many grams, so grams is G, of the second would be required to react completely with 0.66 or 0.600 grams of the first. So we balance 1 chromium, 1 chromium, 2 Cl, 3 Cl. So we need to put a 2 in front of there. So now that's 6 chlorides and 2 chromium. And we need to put a 3 here so we can get 6 chlorine. And then we need a 2 to get the chromium. So now we're balanced. And that's important because we're going to need those mole to mole ratios to change substances. Because we're starting with chromium, 0.6 grams of chromium. We got to go to mole of chromium to change substances. And we want to know how much of the second reagent so we can go to mole of chlorine. And then once mass, and then we can go to gram of chlorine. And how you go to mole to gram is the periodic table. You look at the weight on the periodic table. How do you go to mole? You have to do the coefficients. So that's your plan. Now we just do it. So we start with 0.600 grams of chromium. And then we're going to go from grams of chromium to mole of chromium. That's not what we want. So we got to go from mole of chromium to mole of chlorine. And we want mass, so we copy mole of chlorine down to gram of chlorine. And now we can look at our periodic table and see how many grams of chromium. 51.9961 for 1 mole. Here we have to look at our coefficients. 2's in front of chromium, 3's in front of chlorine, and then for 1 mole of chlorine, and we look at our periodic table, when we do 2 times 35.4527, that is 70.905. So now we do 0.6 divided by 51.9961 times 3 divided by 2 times 70.905. So 1.23 grams of chlorine react with 0.6 grams of chromium to provide the reaction. All right, so the next one, we need to balance the next one. So we have 1 rubidium, 1 rubidium. We have, go ahead and just erase the plan here so we have some space. So one rubidium, 3 oxygens, yeah, 3 oxygens and 2 hydrogens. Over here we have 3 oxygens, 1 rubidium, and 1 hydrogen. So if we put a 2 here, now we have 1, 2, 3, 4 oxygens, 2 rubidiums, 2 hydrogens. If we put a 2 here, we have 2 rubidium, we have 4, 5 oxygens, and we have 2 hydrogens. The hydrogens are okay. The oxygens are not. Let's put another 2 in front of here. just to get it even. So now we have 4 hydrogens. We have 2 times 2 is 4. We have 6 oxygens. And then we have 2 rubidium here. We have 4. So we're going to have to go with 4 there. So that makes that 4. So now we got to go with 4 here. Okay, so we got 4 times 2 is 8. 8 oxygens plus the 2. We have 10 oxygens. We have 4 hydrogens. We have 4 hydrogens. Here we have 4 rubidium. Okay, so the nice thing is we can put a number in front of this oxygen here. So we have 10 oxygens, and we need 10 over here. So we have 4, and then so we need 6. So if we put a 3 here, that's 6 oxygens plus the 4 oxygens. So now let's just clean all this up and see if it works out. Put the 4 and the 4, 4 and a 4. All right, so let's just double check. We got 4 rubidium, we got 8, 10 oxygens, and we have 4 hydrogens. Over here we have 4 rubidium, we have 4 hydrogens, and then we have 6 plus 4 is 10 oxygens. So yes, we have a balanced equation, and you got to start with a balanced equation. And we're going to start with 0.6. Let's just do our plan again. Okay, so we're going to start with 0.600 grams of rubidium oxide, and we've got to figure out how much grams of water. And so we go from grams of rubidium oxide to moles of rubidium oxide, because that's the only way we can go to moles of water. And then we can go to grams of water. And whenever we're doing moles to grams, we need to look at the periodic table for the molar mass. Whenever we're going from mole to mole, we look at the balanced equation for the coefficients. All right, so then we just start. We start with 0.600 grams RbO2. We're going to put grams of RbO2 on bottom for 1 mole of RbO2. And then we're going to go from mole of RbO2. We're going to change substance here to mole of water, H2O. And then for 1 mole of water, we're going to have grams of water. And so now we just need to fill these in. So I'm going to get my periodic table, and I'm going to go find Rb, which is rubidium, and it's in group 1, so that's 85.4678 plus 2 oxygens. So I get 117.468 grams for 1 mole. And then here, there's 4 moles of rubidium for 2 moles of water. We got that from our balanced equation. And then for water, we have 16 plus 1.08 plus 1.08 plus 1.08 plus 16 is 18.016 grams. So now we do 0.6 divided by 117.468 times 2 divided by 4 times 18.016. And I got 0.0460 grams of water. Reacts with 0.6 grams of rubidium oxide. Okay, so moving on, the balanced equation. So is that balanced? Yes, it's balanced. Phosphorus and oxygen gas, so this is combination reaction. What is the limiting reactant when each of the following sets of quantities of reactants are mixed? Now the limiting, so if you're going to make some brownies and you want to make like 24 brownies and the recipe calls for 4 eggs and 2 cups of sugar, I don't know, I don't really make brownies, so, and you only have 1 cup of sugar, but you got 12 eggs, what's your limiting reactant? Yeah, the sugar, because you need 2 cups of sugar. So it takes a certain amount of reactants to form a compound here. And so when you're given 2 sets of amounts, then you know it's a limiting reactant. So you see how you have 2 amounts of, you have phosphorus, and then you have also an amount of oxygen. And I recognize this as 2 givens. And so you're going to have to work 2 reactions, 2 dimensional analysis problems to find out the limiting. And the limiting is always the least. And so what you do is you go from moles of reactant to mole of product. And it should always be the same product. And you're going to do that reactant 1 and then mole of reactant 2 to mole of the same product. And then whatever's the least number of mole of product, that equals your limiting reactant. Reactant is always here. These are your reactants. So your limiting reactant will either be P4 or oxygen. So we have to do that. So let's do the first one. 0.5 mole of P4, and you want to go from mole of reactant to mole of product. So you got to copy that down because you don't want mole of P4, you want mole of P4O10. And then you're going to do the same thing. So what's the mole ratio? 1 to 1. And then you're going to do the same thing with the other reactant because you have 2 givens, you need 2 dimensional analysis. So you're going to have 5.0 mole of oxygen, and you're going to change substance from mole of oxygen to mole of product, P4O10. It has to be the same one. This has a 5 in front of the mole here, and this is a 1. Now, you get your calculator out, and you do 0.5 times 1 divided by 1 is 0.5. Let's keep with the same color scheme. So this is 0.50 mole of P4O10. And then the next one is 5 divided by 5 is 1.00 mole of P4O10. So what is less, 0.5 or 1? So 0.5, this is less. So your limiting reactant is P4. So this is your limiting reactant. All right, we do the next one. 0.20 mole of P4. We'll just do this. 0.20 mole of P4 and 1.0 mole. So 0.2 is 0.2, and 1 divided by 5 is 0.2. So no limiting reactant. They both give you the same number. Okay, the next one, 0.25. Let's just clean it up. Let's do it. We'll do it again. So we're going to do C. 0.25 mole of P4, and for 1 mole of P4, look at the coefficient, we get 1 mole of P4O10, so that would be 0.25 mole of P4O10, and then we have 0.75 mole of oxygen, and for mole of oxygen to mole of P4O10, we have 5 moles of oxygen for 1 mole of P4O10. 0.75 divided by 5 is 0.150 mole of P4O10. Which one's least? 0.15 is less than 0.25. So the limiting reactant is the oxygen. Sodium bicarbonate reacts with hydrochloric acid in a gas-forming reaction to produce aqueous sodium chloride, water, and carbon dioxide. Determine the limiting reagent and mass of carbon dioxide produced when 8.0 grams of sodium bicarbonate is added to a solution containing 4.0 grams of HCl. So we're going to have to convert them to moles. So we have to go from, and we got two amounts, so two-dimensional analysis. 8 grams of sodium carbonate. We're going to copy down grams of sodium carbonate, bicarbonate, baking soda, for 1 mole of sodium bicarbonate. And then we're going to convert the mole of sodium bicarbonate to a product. Well, it's asking for carbon dioxide, so let's go to that same product. So we're changing substances. So we go from mole of sodium carbonate to mole of carbon dioxide, and I just stay there. I just go to the mole, and then I'll figure out grams once I find out my limiting reactant. So we got to look up the formula mass for sodium bicarbonate. So we have three oxygens, 3 times 16, plus a carbon, 12.01, plus a hydrogen, 1.08, plus sodium, which is 23. So this is 84.018 grams. What's our coefficients? Are these balanced? 1 sodium, 1 chlorine, 2 hydrogens, 2 hydrogens. Okay, it looks balanced, so I can say for 1 mole of sodium bicarbonate, we get 1 mole of carbon dioxide. And so 8 divided by 84.018 is 0.0952 mole of CO2. I'm looking for my limiting reactant. All right, now let's go to HCl, 4.0 gram of HCl. We go from gram of HCl to mole of HCl. And then we're going to go from mole of HCl to mole of CO2. And that's where we'll stop. The mass for HCl, 35.45 plus 1.008, 36.458 grams. So let's look at that again. Cl 35.45 plus 1.08. I just want to make sure I have that mass. And then here for HCl we have 1 mole and 1 mole of CO2. So we have 4 divided by 36.458. We have 0.1097 mole of CO2. Okay, so which one's smaller, 0.1 or 0.09? So this is the smaller one. So the limiting reactant is NaC, or sodium bicarbonate is your limiting reactant. And so when it asks how many grams of carbon dioxide is formed, we have to work with this number. So 0.0952 mole of CO2 is formed. And then we convert that for 1 mole of CO2. How many grams do we have for CO2? 16 times 2 from the periodic table plus 12.01. That's 44.01 grams times 0.0952. So we make 4.1897, 4.19 grams of CO2 is formed in this reaction with those amounts. So theoretical yield, well, okay, in a process for obtaining pure copper from copper ore, 55.6 grams of copper metal was obtained. Okay, so now we want to figure out a percent yield from a reaction. And so you want to always do actual yield, which is your formula that you memorize, over theoretical. And then you take that times 100%. So that's your formula. You just do A yield over T yield times 100%. Actual yield should always be the smaller number, because remember, part over whole should be smaller times 100%. So theoretical is what we've been calculating that. We do that when we do limiting reactants and stuff like that. Actual yield, that has to be given to you. That will always have to be given to you. That's something you measure in the lab. So they give you the actual yield here is 55.6 grams of copper metal. A student was synthesizing, oh, so these are two different problems. This is problem one, that's problem two. So let's do problem one. Well, we have to go back to the theoretical. Oh, I'm sorry, this I can't even calculate it. Is this the theoretical yield or actual yield? This is the actual yield. Okay, so we're done with that. Okay, let's go on to the next problem. A student was synthesizing aspirin in the laboratory. Using the amount of limiting reactant, she calculated the mass of the aspirin that should form. That's theoretical yield. That should form is 8.95 grams. So anytime you're doing that calculation with dimensional analysis, that from the limiting reactant, that's going to be your theoretical yield. When she weighed her aspirin product on the balanced, it massed to 7.44 grams. That's the actual yield. So what is the actual yield? 7.44 grams. What is the theoretical yield? 8.95 grams. Calculate the percent yield. Well, you would do 7.44 grams divided by 8.95 grams times 100%. And that would be 7.44 divided by 8.95 times 100. That's 83.1% yield is the percent yield. All right, so our last problems for these sections, the combination reaction of magnesium with bromine to form magnesium bromide is represented below. Is that balanced? 2 bromine, 1 magnesium? Yes. All right, looks like we have a limiting reactant problem because we're given 1.0 mole of magnesium is mixed with 2.0 mole of bromine, and 0.84 mole of magnesium bromide is obtained. That's the actual yield. 0.84 mole of magnesium bromide. What is the percent yield of the reaction? Now, when you do percent yield, it can be gram over gram times 100% because they cancel out, or it can be mole over mole times 100% for your units. It doesn't matter. But what does matter is you got to have the same here. You cannot have gram over mole or mole over gram. That will not work. So we're given actual yield in mole, so we're just going to solve this for mole. So, and that makes it nice because then we do not have to deal with formula masses. So if we have 1.0 mole of magnesium, we've got to go to magnesium bromide. So mole of magnesium goes to mole of magnesium bromide. And that's a 1-to-1 ratio, so that's 1.0 mole of magnesium bromide. And then we do the same thing with 2.0 mole of bromine. And for 1 mole of bromine, we have 1 mole of magnesium bromide. And so that would be 2.0 mole of magnesium bromide. Now, which one's the least number? 1 or 2? 1. So this is your limiting reactant. And so that is going to be your theoretical yield. And so now we do actual yield over theoretical yield times 100% to give our percent yield. So our actual is 0.84 mole of magnesium bromide, and this is over 1.0 mole of magnesium bromide that can actually be formed theoretically. 0.84 divided by 1 times 100% is 84.0% yield. And that is how you do percent yield. And that wraps up these chapter problems.